All right, so let me give you guys the idea of Lagrange multipliers. Lagrange multipliers. Okay, this is a Calc 3 topic that sometimes you tend to forget, which is a shame because it's super duper useful, but only in a certain case. You guys good with that?
Okay.
So we've been doing these maximize, minimize problems, right? So this thing, Lagrange multipliers, is good for problems that are phrased as max, min, f of some stuff with g of some stuff is a constant. Cool. If you're trying to maximize or minimize a function over a closed and bounded set, Lagrange multipliers is probably not your jam. Does that make sense? Like without that constraint piece, without this guy, Lagrange multipliers isn't going to work for you. You can sometimes make your closed and bounded set into one of these, right? And then Lagrange multipliers can be a good idea. You cannot always do that, or at least you can't always do that conveniently, but sometimes you can, and it's awesome. Cool. So, for example, right, that problem we just did, where we did this like, what was that? Minimize the distance squared to 0, 0, 0, subject to 3x plus 2y plus z is 1 or something, right? You guys see that? That's maximize or minimize a function, right? With something equals some constant. You guys all see that? Okay, so let me tell you how this works intuitively. So I'm just going to draw a one-dimensional picture of this situation that we were just in, right? So we had some kind of a line type thing, right? And let me move it off of 0, 0, 0. So let me I'm just going to go A, B, C here, right? So this is the one I told you guys would be just a little bit harder than that thing we just looked at, right? So here's my constraint. That's kind of my g of maybe x and y and z in this case equals some constant k. And then I have, well, I'm trying to minimize square distance, right? So I've got like spheres around this. I'm just drawing circles, but really think spheres, right? And then I'm going to do that thing I described where we're just going to say, well, you just puff it up a little bit, right? And puff it up a little bit more until it hits, right? You guys see that? When it hits, something very special is going to be happening. You guys see what's really special about that?
The g of all the functions becomes a tangent line?
Yeah. You guys see that? Right? This thing is kind of tangent to the blue thing, right? That's really the idea here. Right? So we're going to think to ourselves, there's going to be some black constraint, right? Maybe one black level curve, right? And then there's going to be some kind of like blue level curves. So in a world where I'm not looking at this easy picture, right, where I have some kind of more complicated thing going on, right, I might have my black constraint curve could look like this. You guys see that? And then I'm going to have a whole mess of like blue level curves. And those might look kind of funny shaped like this. And I'm going to keep puffing these out and stop drawing both ends.
So it's not always puffing spheres.
Yeah, so it's not always puffing spheres. It's just puffing whatever your function is that you're trying to optimize. You guys see that? So there are some interesting points in here, and I didn't actually get those level curves. But there's one right here. You guys see that one? There's one that's going to happen on this level curve in between this one and this one. You guys see if I puff that one up just slightly, I'm going to get tangent there and maybe tangent down in there.
Yep. Okay.
So I got kind of an interesting point here, an interesting point there. And then someplace out here, there's that level curve, right? It's going to have an interesting spot on it. You guys see this? So if you're thinking, right, these are your increasing level curves, just for kicks, right? I'm only saying they're increasing for kicks. It doesn't have to be, right? But if these are your increasing level curves, where's the first spot it hit?
Those two.
Yeah, it hit kind of simultaneously at those two spots. And then what happened? We were kind of puffing it up again, right? And then it hit here. And then there were still intersections other places, right? Like this intersection and this intersection. This one happened last, right?
Yeah.
You guys see that?
So you're only concerned with the tangent points, you're not concerned with the regular intersections?
Yeah, I'm only concerned with the tangent points because at the regular intersections, right, like this intersection, say, like why isn't this thing something I'm considering? Well, if it's not tangent, right, then if I puff it up a little bit higher, I can move along the black curve still. You guys see that? That's a point where I can do, right? If I go that way, I can get lower still along my black curve. If I go this way, I can get higher still along my black curve. Those aren't maxes or mins on that black curve. You guys see that? So that tells me I can still keep climbing there. But those tangencies, those are when it first hits, right?
Is that the min?
Those are the mins, right? Assuming that the blue curves are increasing here. And the last point where it hits,
Max.
which is a max. And what's that second one? It's nothing. It's a local max, right? Like it's the best you can do on that side, but I don't have an on that side, so I don't care. You guys see that? It's really kind of a saddle, right? So what's going to happen, right, is we're going to search around for these tangencies. But I've been drawing this like two-dimensional picture, right? But I don't have a two-dimensional picture. I might have a three-dimensional picture or a seven-dimensional picture or shit. Right? So what I have, though, is I have one function I'm trying to maximize and one level curve that I'm kind of subject to, right? So how do I make this idea of tangency into higher dimensional land?
You take the gradient for either, well, both f and g, so you can see whether it's optimized and only f and only g.
You guys see that? Right? I'd take the gradients, but the gradient has this like length information that I don't actually care about, right? Because my concern, right, is like maybe here's the gradient to blue, right? It's perpendicular to the level curves, right? So there's all these gradients of blue that stick kind of straight out from these level curves. You guys see that? But where does the black gradient point?
That's perpendicular to the black curve.
Yeah, it's perpendicular to the black level curve, right? But that's perpendicular to the black level curve. You guys see this? So I have to allow for it to be flipped over and maybe different lengths, right? So I don't want to just take the gradients and set them equal to each other. I want to do, let's see, so I'm going to do blue level curves, gradient of f, right, is lambda, that's some constant, right?
Okay.
Oops,
Could
constant.
have called it K just to make it even worse.
What do you spell constant?
CNST.
There we go. So is lambda times some what?
Times the gradient of your
Yeah, good. You want to make the tangencies, right? So you take your gradient of your function you're trying to optimize and set it equal to some scalar times the gradient of the function that you're subject to.
So lambda is the Lagrange multiplier then?
Yeah, good. Lambda is what we call the Lagrange multiplier. Please keep in mind, you don't have to solve for lambda because no one cares what lambda actually is. You guys see that? The sign of lambda can tell you something interesting, but lambda itself does not freaking matter. Don't have to solve for it if you don't want to.
There could be problems where we would have to, right?
There are a number of problems where it is most convenient to locate lambda first, but you don't have to. You guys see that?
It just allows us to state that they're parallel.
Yeah, exactly. This is just a thing about parallel, right? This is saying that those tangent lines agree, and I don't actually care whether the gradients point opposite directions or have slightly different lengths. As long as they're parallel to one another, that's what I need. You guys cool with this? Okay. Should we try one?
Yeah.
Yeah. Should we try that same one we just did, just to make sure it works? Okay, so let's do the problem that we've done 3 different ways, or 2 different ways today. We'll just make it 3. So we want to minimize distance from x, y, and z to 0, 0, right? Which is x squared plus y squared plus z squared on the line 3x, or the plane 3x plus 2y plus z equals 1. You guys good with this? Y'all remember this is that same problem we've done a million times? Where was this one? This was number 19 and 15.2. Again. But we should get the same answer, so let's do it. So what's the gradient of d? And what am I setting that equal to?
I was saying equal to Lagrange gradient of G.
So this thing's called a lambda, FYI.
Okay.
Lambda.
Yeah, and sometimes they put a little floopy on the top. Right, like all a half-life. Okay, so I'm going to find the gradient of d. I'm going to set it equal to lambda times. Okay, so this is going to be the gradient of your constraint function, right? You best make sure that your constraint function actually looks right. It needs to be some function of the same numbers of variables as your other guy set equal to a constant. Yeah, or less than or greater than a constant. You guys see that? Probably start with equals to, and we'll deal with the less than and greater than cases later. So this guy, right, is that written as g of x, y, and z equals number? Yes?
Yes.
Good. Cool. If you had z equals 1 minus 3x minus 2y, yeah, you got to fiddle it around until you got this. You can get, right, that number on the other side doesn't matter at all. So if you put the minus 1 equals 0 over here, that's totally fine. You guys see that? You're going to differentiate anyway. It's going to drop off anyway, right?
Question, what if it equals 0?
Fine.
It's okay.
Number. Equals number is what you need.
Even if it is nothing.
Yeah, even if it is 0. So, what's your gradient of d?
2x, 2y, 2z.
2x, 2y, 2z. And this is equal to lambda
3, 2, 1.
3, 2, 1. Okay, so there is some creativity required for these, by the by. So you're going to multiply this through, right? So you'll get 2x is 3 lambda. 2y is 2 lambda. And 2z is lambda. You guys all see this?
Yep.
And now we're all wondering,
What next?
we're all wondering why the F is this problem broken? Why does this problem seem broken?
Because we
Because we have
have
4 unknowns.
Okay,
and
we have to
3
remember that
equations.
this.
Good, you have 4 unknowns and 3 equations. This theory can't work. Right? What's wrong with it? What do we F up?
Lambda's a constant. Value. That's
No.
not there.
We don't know what it is.
No. I need to know, I better be able to figure this out. If I just put in a number for lambda, right? Then I'm saying how long that gradient vector has to be in. I have no idea. So I can't just throw a number in for lambda. You guys see that?
Yeah.
If we solve-
Where's the other equation? There is another. Why are you raising your hand, Jordan?
How did you say if we solve for lambda times
Yeah, you can totally do that. You can try to eliminate lambda, but you're still 3 equations into 4 variables, right? So you're still 1 shy. Where's the other equation?
Distance equation?
Not the distance equation. Where I erased it already, so it's not on the board. What is the other equation?
The
Your restraint.
Yeah, the constraint's another equation, right? You guys see that? Right? There should be some kind of g of stuff is k. That's your 4th equation. Don't forget that. I see a lot of students like wander into Lagrange multipliers. You set this up right, and then if you don't notice that you have 4 variables and 3 equations, you can wander through this forever. Right? You just like wander around in the woods forever, not realizing that there's a flashlight in your pocket. Right? So you need that equation for your constraint. So what was my constraint here? Okay, good. So now I have this. So what do you get out of this?
You can solve for variable constraint of the equations.
Yeah, I'd probably solve for
Z.
z. So z is lambda over 2.
minus lambda.
y is lambda. Or do you go through that or?
That's nice. Y is lambda.
And x is 3 half lambda.
And x is 3 lambda over 2. Okay, great. Now, yes?
Can we just plug that into our constraint and then figure out what lambda is through that?
Sure, that'll work. Okay, so take all these, shove them in there, right? So you get 9 lambda over 2 plus 2 lambda plus
Lambda over 2.
lambda over 2 equals 1, which is,
5 lambda plus 2 lambda, 7 lambda.
you guys all see this? Why are there 7s the whole day today? Because I keep doing the same problem over and over again, and it's full of 7s. So you get lambda is,
1 7.
let's see, so I got 14 lambda over 2 is,
7. So yeah, 1 7.
so you get 2 over 14, so lambda is a 7th. So you're right here. So I took these guys, right? So that's what x is, and that's what y is, and that's what z is. Crammed those in there. From that, I got this equation. Now I know what lambda is.
Now plug in lambda into your.
And then you can take your lambda and trot it back and plug it into everything.
And guess what you.
So we get the same points we got before, which is awesome. Cool. You guys follow this?
Let's go.
Plug that into where now?
So I would take this 1/7, right? Oh god, I need another car. Take this and plug it into these guys.
And those are your points?
So that's going to be my point, right? And there's only going to be one because it's boring, but. So I'm going to get my point that's 3 times a 7 over 2, comma, a 7, comma, a 7 over 2, which is my 3/14, 1/7, and 2/7.
1/14.
1/14.
1/14. That's
1/14. 1/14. Thank you. 3/14, 2/14, and 1/14. Cool? Questions, Steele? So how do I know this is a minimum?
Because lambda's positive. I just threw that out.
No.
Let me see.
Because I don't think that tells us much about the saddle though.
That tells us.
Is it because our original function we're optimizing is positive?
You could go back to the original function and look at it. I would probably say that you're.
Well, pictorially it's in a plane, and then the constraints sound like a whole shot.
Yeah.
So that's going to be quadrant 1, since the plane is positive in all positions.
Yeah, so I think your best bet is to do this thing where you kind of look at the function and the constraint and say, okay, the constraint's a plane and its normal vector points away from the origin. And so as I'm growing this distance, that lambda is positive here, which says that this is agreeing, right? Yeah, so if you have kind of weird looking, right, then you can take this, right? This is going to give you some value under your d function. You're going to evaluate this, and then pick any other point at all, and evaluate the d function there. See that this is smaller. This is going to be a minimum. In practice, what you end up with on these is like, you'll do this whole rigmarole, and you'll get like a couple of options, so a couple of points. Plug them all into the original function and just order them from biggest to smallest. Cool?
You said that sometimes you wouldn't need to find lambda. What would be a situation in which you just don't find lambda?
You could actually do this one without finding lambda. Do you guys see how you could do this without finding lambda?
Yeah.
I mean,
Do
we
y
did it.
instead.
Yeah, so instead of doing lambda's y, right, and plugging lambda into the equation, you could do y as lambda, and so z is y over 2.
Okay,
and x is 3y over 2, and you would get identically this, right? And then you would never know what lambda is, except that it's also actually y, but you didn't have to realize that. You guys see that? So if you can get those freaking lambdas out of there fast, I would kind of advise for that. If you can dump that thing to start with, it's one less variable you have to deal with. Cool? All right.